The examples are you have polar coordinates, cylindrical coordinate system. Okay, these things will you just rush it. Polar coordinates. Second one is cylindrical. And third is spherical. These are the standard ones. Spherical. Okay, so spherical coordinate system. So what we have is, for example, x is given as x of u v w. So these are the general ones. Okay, so y equal to y of u v z, u v w, z is z of u v w. So what was an issue in the last class? Thing is, suppose you have a surface. You have a surface like this. Imagine there is a surface like this. Okay, so this is like a z direction. Okay, so z direction. This is your x y. So for every x y something, so this is the corresponding surface. Z equal to explicit. If you say this is the explicit surface. Otherwise, if it's a function of x y z equal to 0, that is our constant. That is the surface. So what happens is that at every you pick up a point in the space. So it is also on the surface. There is a surface on that. Okay, let's pick up a point on the surface. Then in the calculus, you have seen there is something called tangent plane. There is a tangent plane, right? So the tangent plane passing through this. What is the tangent plane? Basically, total derivative will give you that x into x minus. This is actually x naught. So corresponding value is x naught, y naught. So you have x naught, y naught, z naught. That is f at x naught, y naught. So this through this point, if you actually draw a plane, so that is actually giving you the tangent plane. Now, what are those that involves in terms of those partial derivatives? This is a so okay. So the tangent plane will have all the tangents, right? Passing through this point, all the tangents, all different directions you have a tangent. So those tangents, how do you pick up? So you pick up those tangents by considering a curve. Uh, okay, so if you want in this direction, you just consider a curve passing through this on the surface, the tangent in that direction. So that should be a tangent in that direction. That is actually direction derivative along this direction. Okay, so if you take this direction to be x-axis, so what is that you get? So you want only x direction. So only these values if you consider. So there will be a curve passing through this point, which is whose tangent at that point will be parallel to x-axis. Okay. So of course here is y-axis. If you want x-axis, you have to put it this way. So if you want y-axis, do y. Okay. So what is the derivative? Basically, what is the direction derivative? That's actually tangent is actually direction derivative. That is actually gradient of this function, this whole thing. So gradient of f and minus 1. Okay. That is it's basically normal towards in this direction. So towards the x direction means 1, 0, 0. That will give you dou x. So that means dou x is actually giving you, that's a tangent for this surface along this x direction. Okay. So in a similar way, now what I consider is this in the if you consider the xy, right? So through this x naught, y naught, z naught, any point, I will have once you have this coordinate system, I will have just like xy plane, yz plane, and xy plane, xy, xz, and yz plane. At every point, there are three surfaces. So all these three surfaces at that point, you consider curves whose tangent at that point along the x-axis. Basically, you're asking for each of these three surfaces. If you are considering the direction derivative along the x-axis, okay, that is exactly what we were doing earlier. So dou x, right? Dou x by dou. So if you write it here, what we did is so if you see this dx dy dz, dx dy dz. Okay. So what are these dy dz dz? So basically, so these three components. So if I write like this is actually total derivative, right? So dou x by dou u dx plus dou x by dou v dv plus dou x by dou w dw. So this is one component. Okay. And then you have also other components like, so this is one, and then similarly dou y by dou u du dx du. Okay, sorry, this is du dv dw. So this is also dy by dou y by dou v into dv plus dou y by dou w into dw. This is another one. So the next one is dou z by dou u du. So basically you're writing dx dy dz total derivative for these functions. So dou z by dou v into dv, dou z by dou w into dw. So now this is the tuple. Okay. So this in the vector notation, this is actually you're calling the dr. This is the position vector dx dy dz. Okay. So the dr is the position vector of dx dy dz. So this is equal to what do you get here? So this you can put them together. So you have dou r by dou u du plus dou r by dou v into dv plus dou r by dou w into dw. Is it fine? Now, can you see? Can you now feel it that x equal to constant, for example? So x equal to constant at every point x y z. At every point in the space x y z, you have this will be constant, right? So this there will be some planes passing through the point. For example, at every point, x naught, y naught, z naught, that belongs to R3. Okay, uh, three planes. What are those three planes? X equal to constant, y equal to constant, z equal to constant. Pass through x naught, y naught, z. Can you feel this? Hello? So for each of these surfaces, if you consider the partial derivative with respect to, for example, okay? So that means dou u by dou x by dou u, okay? Dou y by dou u and dou z by dou u. So what is this one? It's actually dou r. It's a vector. This is the partial derivative of that vector is equal to this one. This is a tangent. It's a tangent to tangent vector, right? So this is the tangent vector to the not to these three surfaces. Three surfaces you are writing, no? So finally, when you calculate this one, dou u, dou y by dou u, these are the vector to the curve that varies with u. That is coordinate curve. Coordinate curve. Curve. What is the coordinate curve?
X equal to, sir.
From the surfaces. What is the surfaces that you get? For example, x-axis, how do you get it? X-axis,
X
how you
equal
are
to,
getting? Yeah?
sir. X equal to, no,
See, x equal to constant line, how do you get? Basically, you use your z equal to constant. That is xy
yes,
plane,
sir.
xz plane. So you cut these two surfaces, you will get your this curve, x axis. I'm not saying x equal to constant you will get. What you get is x axis you will get if you take the intersection of these two surfaces, each of you have three surfaces here, right? So you consider intersection of these two surfaces at a time. If you consider, you will get the coordinate curves. So for example, x-axis you will get by the intersection of y equal to constant and z equal to constant. Okay. So what is that you have there in your thing? So in your plane, what is that at every point? This is the Cartesian coordinates we are writing, right? This is the Cartesian one. And what happens to this one? So what exactly your surface is here? The coordinate curve from the surfaces. What is that you get? V equal to constant and W equal to constant. Isn't it? See, these are equivalent. You have x, y, z Cartesian coordinates. Now you have u, v, w Cartesian coordinates. Something similar to x-axis, you will get y equal to constant, z equal to constant. You will get v equal to constant, w equal to constant. Two surfaces, wherever they intersect, that is actually your x-axis replacement. That is u-axis, u curve. That is called coordinate curve. Coordinate curve, u. Okay, from the surfaces, from the intersection of surfaces, intersection of the surfaces. U is, if you want, you can put it as U is the intersection of this surface. Can you see this one? Something similar. So that implies similarly dou R by dou V, dou R by dou W are tangent vectors to the coordinate curves. Coordinate curves V and W generated by the intersection of surfaces whatever the V, if you want, basically U equal to constant and W equal to constant. Okay, and what is the W is U equal to constant and V equal to constant. Do you understand?
Yes, sir.
Okay, so now you take some example. If you take some example, you will understand. So you simple example that you consider, whatever you have written. So basically, you have to understand that for a surface, direction derivative along the x-axis will give you. So here along the u axis, if you take, that is basically will give you that gradients dou r by dou v, dou r by dou u will give you along the u in that direction. Where for the coordinate curve at that point, if you take the as you along that curve, you will get basically that is a tangent. Along the curve means what? It's basically tangent, right? The direction of the curve. Direction along the curve means basically tangent curve. So that's what it means. So that's why you will say that these are tangent vectors. For example, x equal to r cos theta, y equal to r sin theta, z equal to z. So what is that you get here? So dou r by dou r by r bar means dou r bar means dx dou x dx dy dz. Okay, so with respect to x. So this is along r direction if you do. So what is this one? This is actually cos theta, sin theta, and 0, right? So you take, for example, this is you forget about the z direction. So this is r, for example, cos theta equal to 0. What you are getting is 1 comma 0. So that is in this is the tangent, right? So this is your tangent. This is actually radial direction, right? So if you change your theta, this is your radial direction. So this is basically your radial direction, r direction. Okay, direction of r. So for fixed different theta. So this is what is the tangent. So this is, so whatever you do, all these are radial directions, isn't it? For all theta, these are all radial directions. You're only varying along this radial thing. You may not see a simple one curve in the Cartesian coordinate system. So what happens here? Dou r by dou theta. But just think that theta equal to 0. So what happens here? So here in this case, dou r by dou theta means minus r sin theta, r cos theta, dr anyway, z anyway will be 0. There's nothing to do with theta. So in this case, what happens? So if you actually see at this point, theta equal to 0, one is this direction, the dou r by dou r, okay? Dou r bar divided by dou theta will be actually theta equal to 0, 0 comma 1. That is actually in this direction, 0 comma 1. So basically, you are considering all different. So at this point, this direction. So for different r, you have a different, that same direction, theta, okay? At this point. So why I'm considering theta equal to 0? You are basically considering the point. Theta equal to 0 means x equal to r, y equal to 0, and z equal to z. So any point in the space you consider. So these are the two directions you got. These are actually tangent to the curves. These are your theta varying curves, right? Theta varying curves are circles. Z varying curves are all. These are all your Z varying curves. Okay. These are your curve. What is that? Coordinate curves in the cylindrical coordinate system. For Z what happens? Dou R by dou Z is simply 0, 0, 1. Dou R by dou Z is actually, so you do it 0, 0, 1. So that is actually perpendicular to this. These are in the plane, and whatever perpendicular, that is anyway Cartesian coordinate system. So these are basically, you can see that these are tangent to the curvilinear passing through the point. Once you fix your point, then this r and theta and this z are fixed as z, x naught, z naught, y naught, z, x naught, y naught, z naught. So at that point, for example, I fix theta equal to 0 and r equal to 1 at this point, and z, if you fix z equal to 0, that's still the 0, 0, 1 is anyway there. So at this point, 0, 0, 1 in the space, if you consider this one, this is actually 1, 0, 0, right? Yeah, sorry, this is at this point you are doing. So at this point you are doing 1, 0, 0. So if you actually see dou x by dou r is basically the vector uh, 1, 0, 0, right? 1, 0, 0. So here, if you consider dou r by dou theta, is basically that is a vector. What is that vector we get here? 0, 1, 0, and the other one will be 0, 0, 1. Can you see that one now? Those are the tangents in R3. You just apply to this, you simply can see that one. So the same way, dou R by dou V, dou R by dou W are tangents to the coordinate curves. Now let us look into. So any questions up to here?
Sir, for del r by dou r by dou r is following a radial direction, and dou r by dou theta is following cylindrical direction. As what type of direction, sir?
No, that is actually tangents to this circles. Those are
Okay.
tangents to these circles.
Okay,
Circles,
sir. Okay, sir. Okay,
circles
sir.
and rays. Okay, and then
Oh,
z axis will
okay, sir.
be z. Okay. Yeah. So now let us look at this. What is exactly what you got? dr. Now what we have is dr is equal to now dou r by dou u du. It's dou r by dou v dv plus dou r by dou w dw. This is what we have. So these are your tangent curves along the coordinate axis. So dou r by dou u is nothing but modulus of, this is a vector, right? So you say that this is a vector, dou r by dou u, it's modulus into, you call this whatever the direction of along this coordinate curve, you call this simply EU. Just like IJK, I'm just trying to represent this as EU. Okay, so EU basically it's a vector direction. Okay, so this one, and then dou r by dou v is actually its amplitude, that is dou v into EV. There's no dot. Okay, so just writing. Okay, so like this, and similarly dou r by dou w equal to its modulus dou r by dou w into EW. Okay, so these are vectors, so just represent. Now onwards I will not write, but right now I'm writing. So if you use this one there, you call them. So let's call this as HU. Okay, you call them HU, you call them HV. So these are numbers, so that you don't have to write every time HW. So if you replace this one, what you are getting is dr. So the dr total derivative is equal to this HU into this vector. I'm writing HU into EU. Okay, HU du already there. So HU EU. Okay, this is a vector plus HV dV into EV plus HW into DW into EW. This one. Can you see this from this? I'm just replacing this with EV. EV I'm writing at the last. So you get this one. Okay. Now you can apply to your whatever now. So how are we going to use? Either del, all those examples you can use. So for this example, for example, if you are using for example, x equal to r cos theta, y equal to r sin theta, z equal to z, cylindrical coordinate system. What happens to your HR? You have UVW or r theta z, right? So HR in this case will be equal to, what is that you get? Modulus of dou x by dou r, that is cos theta and sin theta. Okay, so you will get simply 1. So h theta, that is hv, this is actually modulus of the vector. Of course, 0 is there. Okay, I didn't write 0. So polar coordinates you can write 2. So here vector right. So the sin theta comma 0. So here minus r sin theta, r cos theta, and this is 0. So this will be simply r.
Yes.
Okay. Similarly, you will get hz. Hz is basically the modulus of this is 0, 0, 1. That is anyway 1. Okay. So you are getting these things. Then what is a dr in polar coordinates? This position vector total derivative is nothing but you have a du, that is dr. H of hr is 1. hr is 1. So you have dr times hr into dr, that is 1 into dr, into, so that er vector. So that is the unit vector along the radial direction, plus now what you have? So h theta into h theta into d theta, right? So that is r d theta into e theta direction. So these are basically unit vectors. Okay, so you can write this as unit vectors. So where EU, EV, EW are unit vectors. Though we are writing bar, so it's basically should be cap. Okay, so this is this one plus z is 1 bz. What is this direction? EW, EZ direction. Let's put this as 0, 0, 1. Okay, so this is what is your dr. Okay, so dr, you know where do you use this kind of thing? These kind of things we use it for now. If you have a vector f dot dr, integral f dot dr means you can use this. So sometimes if you are using a line integral along some curve. So what is the ds? ds is given as, usually right? So that is dr dot dr, or dx square plus dy square plus dr square equal to dx square plus dy square plus dz square. Okay, that I am writing it as dr dot dr. So this is actually square root of dx square plus dy square plus dz square. There is a space term. You are just trying to write it as space term in terms of dx square plus dy square plus dz square. So this, if you write it here, you are writing dr square. Okay. So what is that you get here? So instead of dx, what do you have here? You have here dr square, square root of. So what you get here is dr square. Instead of x, you have dr square plus dy r square d theta square plus dz square. Simply dz, in the place of dz, you have only dz. Okay. So ds. So this is what you have to put it. Okay. So if you are doing something like f of x, y, z, some or r theta z, okay, over some curve gamma ds. So ds place you have to write this. Okay. Of course, you have to, once you parameterize this s, then you will have to write ds by dt divided by dt. Okay, that's what you do. Followed? You must have done, right, some line integrals. So that is where it's useful. So in this context, you have to use. So that's why let me write it. Let me keep this. So in this context, you'll have to write ds by dt into dt. Once you parameterize gamma, in terms of t, this is also function of r t theta t z t over gamma. So gamma t is parameterized as gamma is nothing but r t theta t z t for t belongs to r. So this is going to become minus infinity infinity if you have depends on where the curve is. The gamma is there. Gamma can take any interval. Okay. Once you parameterize. Without parameterization, you ignore this dt. So what you have a ds is square root of x square dr square d r square d r square d theta square plus dz square and so on. So this is for line integral. So you may be using surface integrals also, right? Surface integrals or what is the surface area? For example, surface area on that surface area, for example. So you want a surface area, ds. If you are dealing with the surface integral, so you have a ds, right? So what is the ds?
The root of.
No, no. See, ds is basically in the coordinates, Cartesian coordinates. That is simply dx dy, right? So what is dx here? So this is the surface. Uh, surface, for example, z equal to constant. Okay, z equal to constant is the surface. Okay, z equal to constant. ds surface element on the surface z equal to constant. So what is this one? This is actually equal to, you have to write, see, surface element in the z equal to constant means in the Cartesian coordinates dx dy, right? So you are going to write here dx dy. What is dx plus? Dx plus what do you have? Dx into er, right? That is simply dr only. Dr r d theta dz, right? So you simply write. So in the case once z is constant, dz is anyway won't affect. So what you have is simply r dr d theta. R first of all dr into r d theta. So that I am writing it as r d. Okay. If you want, you can order it so that you understand exactly what is happening there. So first dr into r d theta. That is your dr d theta. So on a different surface element ds on r equal to constant. What is r equal to constant? Surface. What is r equal to constant? That is on the cylinder. Right? Cylinder surface. ds equal to, what do you get here? R equal to constant means r d theta into dz. Okay. So ds on theta equal to constant, for example, if you want on this surface, what is the surface element? You have to put ds as what is ds here?
R D R dz.
R dr dz. There is no r, no? There is no r.
Yes, sir. Yes, sir. Yes, sir.
R d theta comes from the theta direction, right? So you don't have, so simply dr dz.
Okay,
So
sir. Yes.
that you can see, no? Theta equal to constant means what? It is it's like a plane only, no? It's a ray. Each ray you consider for all that. So it's a basically plane only. Plane obviously dr dz. Okay. So like this you can see, you can feel this the surface element. And of course you also have a volume. If you are considering some volume in this coordinate system, du, dv, dz, right? So that is actually, it should be du, dv, dz. Basically, originally dx, dy, dz. In the place of dx, you have in this case a volume element. Okay, so let me write volume element. Volume element dv is equal to dx, dy, dz. Okay, in the Cartesian coordinate. So dx is dr. That is your dr and r d theta and here dz. So basically r dr d theta. So this is 1. Okay. So like this you can do. So this is for this example. So in general, in your polar coordinates, general coordinates, general coordinates, curvilinear coordinates, I'm writing dv as. So how do I represent my, what is that you got? For example, now go back to this one. What is your dr? Dr, this is what you have, right? This is what is your du, right? This is what is exactly what you call whatever dx. This is your dx, dy, dz, right?
Yes, sir.
Yeah. So how do I get my this quantity? How do I get this quantity dx? You make a dot product with EU, right? dr, if you do, these are all unit vectors, right? EU, EW, EV are unit vectors. Implies dr dot EU, okay? Dr, that vector dot EU unit, okay? They're all unit. So you need not write. Okay, now onwards. So this will give me HUDU, right? Isn't it?
Yes.
HUDU.
Yes, sir.
HUDU, and similarly dr dot EV will give me HVDV. Dr dot EW is actually HWDW. So what is your dr in that case? Dr will become HUDU. I can replace this one. That is dr dot EU into EU. That's a vector. This is a constant. HUDU only. I'm replacing this plus dr dot EV into EV. So some number into the vector plus similarly dr dot EW into EW. So what is your dv in general? This, right? So or basically this one, this whole vectors. Say either you take dx, dy, dz. Okay, this is also okay. So if you do that, what do you get here? So hu, du, hu, hv, hw, du, dv, dw. This is one way of looking at it. Otherwise, if you want to consider as a vector, vectors, how do you represent? Unit volume, unit, what do you call this? Uh, unit cube in space. Okay, around 0, 0. Okay, 0 is one edge, 0 is one vertices, and along the x-axis, y-axis, and z-axis up to 1, 1, 1, 1. That is basically the volume of a cube generated by unit vectors I, j, k. So how do you write dv? Dv also I can also write I cap, okay, I vector dot product with j cross k, right? These are like the word, the box of ijk. Okay, this is also called box of ijk. You must have learned in ijk, right? This is a notation ijk. If you do this box notation in your vector calculus, these are also basically gives you unit volume of unit cube. Okay, so for example, du, dv, dw. So this is actually, so keeping this in mind, so dv in general coordinates I can write like dr dot eu. This is a number into eu dot with the product. Now I write it as a product. What is that one? This is the other vector. The other vector is dr dot ev into into ev dot cross product with dr dot w ew into ew. Okay. So anyway, these are all numbers. These are all numbers. You can take it out. So those are your HU, HV. Okay. So dr dot ew into dr dot ew ev into dr dot ew. So what do you have here? These are all unit vectors, just like ijk. So which is equal to 1. Okay. So what you left is 1. Okay. So what is this one? This is actually dr dot du is hu, hv, hv, right? It also hu, hu du, hv dv, hv, hw dw. So this is the same as hu, hv, hw, du, dv, dw. This is the volume of typical element in the curvilinear coordinates. Is the volume of what do you say? Curvilinear. So you don't say it's a cube. It's a cube. Of you simply say in similar terms, cube in curvilinear coordinates. Curvilinear coordinates. That is UVW. So cube of x direction. Okay, so what is the cube length? U direction, length in U direction, length in U direction, HU du. Okay, so length in V direction, HV du, and so on. W direction, HW dw. So that's what you are just putting as a product. Okay, you understand now? Hello.
Yes, sir.
So that is what is this one. So clearly ds in the general terms, surface also in the we have written for only cylindrical things. So for this u equal to constant if you take hv hw dv dw. Okay, this is basically surface element on the surface on u equal to constant. This similarly ds v is hu hw du dw dsw equal to hu hv du dv. Okay, like this you can give first. These are the things now you can use all the integrals that you see. Okay, all those elements, and then you can use your anyway. So once you have those surface also now will be in UVZ plane, UVZ space. Okay, those in this coordinate system you can always do line integral, surface integral, volume integrals, double integrals, everything. Now, the main objective of this is basically we have equations. Vector equations, right? So for fluid dynamics, so we may encounter gradient and dot the divergence, okay, divergence of a vector, okay, and then you may see that del cross u, all these kind of quantities, okay, gradient of f, del dot u is a vector, so del cross u is a vector. So these are the things. How do I represent? How do I represent these things in the curvilinear coordinates? This u and those the one in the curvilinear coordinates are different. So this is simply a fluid velocity here, u bar. Okay. So these are the things we encounter. We encounter in fluid mechanics, fluid equations. So in curvilinear coordinates, how to represent them? That's what we do. So normally gradient of f in Cartesian coordinate system is dou f by. So what is dou f by dou x, right? So dou f by dou x, dou f by dou y, dou f by dou z, right? This is your curvilinear coordinate system. So what we do is this implies generally that gradient of f dot dr. This is your radial. This is actually your direction derivative. Direction derivative is actually will give me r. This is actually along this position vector direction. If you do, this is actually total derivative df, right? This is the total derivative. At this point, do you understand? So now I am trying to get my gradient of directly something in this fashion. Okay. So let me see how we do this one. So gradient of f dot dr is actually df. Okay. So but df we know this is df is dou f by dou x, but total derivative equal to dou f by dou x into dx plus dou f by dou y into dy plus dou f by dou z into dz. So this is nothing but your gradient. So gradient is, so this is your del f. del f dot dx dy dz. Okay, so that is your LHS. Okay, so these two are same. So we're going to put this way, how we get in a curvilinear coordinates. So how do we put this curvilinear coordinates? So I'm going to write df. F is simply some scalar function, but it's given in terms of f is a function of u, v, w. Okay, so here f is a function of x, y, z. So this in this case, what is df? Df is actually yeah. How do I write this one?
Del F by del U.
Del f by del u du plus del f by del v dv del f by del w dw. Right. So this is equal to now what we can replace is I just multiply because hu du hv dv that we know something. So we divide and multiply hu here. Dou f by dou u into hu du. What is hu du? Hu du, right? If I divide, I have to multiply it, right? Hu du is nothing but dr dot eu, right? So that I will write it here. So hu du is I have to write hu du. If you want, I'll write it as another one. So let me write hu du plus 1 by hv. I divided some quantity dou by dou v as it is. Here hv I divided, right? So I have to multiply hv dv. Hv dv is one term. Like that you do. So 1 by hw dou f by dou w into hw dw. I just multiply those quantities. So this I can replace with 1 by hu dou f by dou u. This is one quantity. This I can replace with eu. So dr. Okay, so this is what we are writing. So plus 1 by hv dou f by dou v. Here also ev dot dr plus 1 by hw dou f by dou w ew dot dr. That's all. Now it is in that position, similar to that earlier. So this is whatever here you can write it as 1 by hu dou f by dou u into eu. Eu is a vector, right? Eu is a vector, so I can put this as vector notation. If you write it, so you go to sum, no, I plus j plus k. So here hv dou f by dou v into ev plus 1 by hw dou f by dou w into ew. Okay, these are vector. Dot product with dr. If you do, that becomes simply sum. Okay, so that is actually your what is dr? Dot product with dr. Dr means what? What is dr? Dr basically what do you have? Du, dv, dw, right? This is basically dr, right? Or dx, dy, dz. Right? That is your dx, dy, dz, right? So that is dx. Dr is basically dx, dy, dz. So you are basically what you are getting is df, total derivative. Left hand side total derivative is what? U is that I can replace as finally function of x also, because these are all transformations, invertible transformations. U v w to xyz, xy to u z. So df is nothing but gradient of f dot dr. Here dx dy dz. Here also I can see both are same, dx dy dz. So here in polar coordinates, what you are getting is 1 by hu dou f by dou u eu. Yeah. So basically this is also kind of gradient of f in UVW. Okay, Cartesian coordinates dot dr. You can think of this as dr as du dv dw. Okay, du dv dw also you can think, because these are all invertible, right? So here this dr here left hand side is dx dy dz. Okay, this is an xyz. Now this is your right hand side is basically u z. Everything is in u z. So this this bar plus 1 by hv dou f by dou v ev plus 1 by hw dou f by dou v dou w into ew dot product with dr. So now we can apply both sides. We can convert this dr in a UVZ. I can convert it finally. Dr is same as dr only there, right? Yes. Originally, dr is basically dx dy dz only, no? So it should be.
Yes, sir. Then, sir, how dr equal to du dv
No,
dw?
that's not. That is actually dx dy dz only. We didn't do anything.
Yes, sir.
So now that's why both left hand side, right hand side, we can make it same. So whatever the quantity implies, this gradient of f originally earlier x, y, z coordinates, now in polar coordinates, we should be in this one. So 1 by hu dou f by dou u du plus this is a vector. So 1 by hv dou f by dou v into ev 1 by hw dou f by dou w into ew. Okay. You remove these unit vectors, basically you can write it as a tuple. Triple. Okay, so the small tuple only, right? You can put it as a tuple. So that's what is this. So you can write whenever you see this gradient in your Cartesian coordinates, you'll have to replace depending on your uh, coordinate system. Okay, curvilinear transformation like x equal to x of uvw, x equal to r cos theta, r sin theta, z equal to z if you use, that is your polar coordinates. W will be z, v equal to theta, this u will be simply that r. Like that you can represent. Now gradient you could do, and you can also do dot product. Okay, so I think next class we will do how to do dot this one. Okay, some vector. So let's not write this u. So let's write it as something else, some other vector field. Let us say f, and del cross f. Del cross f you will do, where f is a vector, right? So you will write it as a vector. I will write it as, so f is in a, I want functions of uvw, right? So uvw means vector product means I will have a f1 of uvw into u direction. Okay, plus f2. You call this f2 of ev plus f3 of ew. So this is now everything is function of uvw. So where is this one? So these two we'll do in the next class. Okay. Come on. How do we represent
Okay, sir.
coordinates? So we'll do this one. I think we'll finish next class. Next we'll return to equations. How do we derive the equations by conservation laws? To start with the mass conservation, momentum, and whatever is possible in the simplest cases like inviscid flow, inviscid fluid we'll do first. We don't consider the viscosity, so that is the Euler equation. So we'll derive one by one. And these things, whatever we are doing in the curvilinear coordinates, either spherical or cylindrical coordinate system, you can actually do, you can actually convert all this. Once you derive those equations in Cartesian coordinates, you can convert them by using these things. You don't have to remember these formulas, but you should know how to derive. So you keep it at one place, tabulate it, and you use it, and so that you can use at least cylindrical coordinate system or polar coordinate system. You should be able to handle what is the gradient of f, those things. At least you should remember. Spherical you need not. Okay, so you tabulate them, and whenever you require to use, then only you have to use. You don't have to write, I want to represent all those equations, whatever fluid mechanics equations into this different coordinate system. You can't use it, you can't remember the everything. So polar coordinates, at least minimal, you try to understand, and because we do mathematics on that, right? So when you're doing in the two-dimensional flows, XY plane only if you are interested. So there you have a polar coordinate, two-dimensional flows. Three-dimensional, if you consider cylindrical coordinate system, maybe it's easy to remember, but not the spherical and other any in general thing. So you derive it, and you should know how you derived it. That's enough. Okay, you tabulate it. That's why generally fluid mechanics books you tabulate it. They tabulate and leave it there. Okay, so we'll see you tomorrow at 10. Any questions up here? Any questions?
No, sir.
Okay, fine. Yeah, we'll see you maybe next class tomorrow.
Okay, sir. Thank you, sir.
Bye.